let us first take a look at what we finished with, if Ryan will open a merge in place that H, and let's go to the very end. That was our crowning achievement. We wrote this sorting algorithm. Remember this one? And in many respects, it's very good. As we shall see, let us look at what is good about it, and then let's find out what is bad about it. So what is good about it? First of all, it's a stable sorting algorithm, which is in place. It uses no extra storage at all. Whether it's wise not to use any extra storage or not, but that's what it does. It does not, any place, rely on existing storage. Then it is polylogarithmic. It's n polylogarithmic. What its complexity? Anybody could tell me? No, not quite. Let us think about it. What is its complexity? First of all, how many levels are we going to have of just sort? Here we're going down recursively, right? Log n, we're splitting by factor of 2. So it's going to be log n levels. And in every level, we're going to have this merge in place. And it's going to be, as it were, like either one merge or two merges or four merges, if you see what I mean. What is going to be their complexity? I'll, at least simply speaking, I'm going to lie a little bit. At the very top, but I'm going to make it slightly worse than it is, it's going to be n log n, because merge itself is n log n-ish. It does divide and conquer, remember. So it's log n times n log n, which is n log square n. It's not quadratic. It's not bubble sort. We're in a respectable sort of area of almost, we're probably doing fewer comparisons than shell sort, a reputable sort. But nevertheless, we're doing a bit too much work. But then, so what are the pluses? The pluses is that it's in place. The pluses is that it's stable. There is another amazing plus, which sort of people who don't think about generic programming don't pay any attention. But we should, because we do pay attention to generic programming. What's the requirement on the iterator? Forward iterator. That is, we will be able to sort anything, literally. These will sort. Singly linked list, doubly linked list, vector, whatever. This is nice. But might be a little bit slow. And what does it mean a little bit? If Ryan will go back to the thing, I did some tests. Back to the previous script, to this. This, I ran a test. There is a harness there, so we could run tests. And this shows for different sizes how stable sort works, stable sort in STL versus in place sort. And what we see, we're gradually sort of getting to be slow and slow. We're not terribly slow, but we're about factor of 6 slower.
What are the numbers in the columns?
These are prorated numbers. These are microsecond per element, or nanosecond per element. Nanosecond per element. So obviously, as the size increases, you have to do more and more work because we're not linear. We're n log n-ish, whichever way we go. But here there is an additional coefficient. So roughly speaking, we're doing something like 7 times slower for fairly large arrays of 2 megabytes. All right?
These are random access structures? Not lists.
These are arrays. But sort of what it shows that this is highly optimized library code. Here we could sort of cheat. We could sort of see how well could be done by, I mean, it just so happens that the same guy wrote both pieces of code. But it's a historical accident. This is long, long, long ago. This is last week. So the question is, and that's what I would like to do, I actually claim this code which we wrote is awfully good. It possesses many wonderful properties. Could we do something to move one toward the other, to make it as fast as the library one, or faster, or not much slower? Right? And that's what I decided to do. I decided slightly to change, I talked to Ryan, I talked to Parama, I planned to talk to you, but somehow didn't get around. But my plan is that what if we, right now it's a small group, I think everybody who is still remaining in the class is sort of hardcore. So why don't we try to, together, to take the code which we had last week, which in some sense I just postulate is good code. It's a good basis on which we could get to fast results, and figure out how to make it very fast. We could do measurements, and instead of, it will be almost like, remember the spoon? But right now I want to use a stronger spoon, meaning I am going to work with the class, but I will not always tell you the truth. Meaning I'm not going, before I was saying let's write this routine, and that would line by line sort of. Here I'm just going to say let us derive together, and we'll have a conversation. But if you go on the wrong path, I might not necessarily stop you. Do you understand why? Because like in real life, I'm not going to stop you when you sit there write code. So let us try together turn what we have into really very fast code by using all kind of brilliant algorithmic ideas. Okay? So to start with, we need to figure out what are brilliant algorithmic ideas. So Ryan will open a file called ideas.txt, and we will write brilliant algorithmic ideas. Okay, idea 1, you have to put period after 1.
Use some extra storage when the size is too.
Use extra storage. And what are you going to do with extra storage?
Instead of doing merge in place, merge into the extra storage and do copy.
Okay, let's write. Let us write what you said.
Since we're repeating a merge multiple times, would you merge in one space and then merge back on your next iteration?
That's another possibility.
Say that again?
That has.
Use the extra storage to merge one of your sub problems into that space, and then on your next merge it back into the original space. So basically you're using it as an intermediate point, rather than do your merge into a new space and then copy it back.
What else could we do? Let's just milk this. No, this is a good idea. It just Yes, we absolutely need stability, and we want to keep. Let us come up with good sort of requirements. Let's come with a set of requirements. What do I mean? We should not turn into bubble sort, right? This is probably a requirement, but that is, what do we want to do? Why? Remember that sort of one of the main advantages of what we have was that it was stable. Is it something we want to lose? I don't think so. So we want requirement stability. Yeah, generic. How generic?
Generic.
Forward iterator says, I mean, it could be weaker than forward iterator. Weaker than forward iterator is input iterator. And it's sort of hard to sort things when they disappear, right? So forward iterator, that's the design. Maybe we'll figure out that we have to drop some of these requirements. What else do we want?
Use limited extra memory or no extra memory.
Bounded.
You said something good. Just no, I wouldn't say that. A limit is a good term. Reasonable, yes. Reasonable. So we don't want, again, sort of here, I think when we think about it practically, we're practical people. Well, at least some people here are practical, not me. But say, are you a practical person? He is a practical person. As a practical person, he said, the requirement of no extra memory at all is bogus. He always has some extra memory. And in reality, by the way, what is happening is that with modern systems, we often have more memory than we need. Because sort of memory keeps coming, but there are other things we have to sort of parallelize our stuff. So we cannot put too much data on processor for other things. So we typically actually have memory. But on the other hand, we want to be reasonable. If we don't have enough, or if they don't fit in cache, we want to have some control. So I think the reasonable is a good approximation. All right? What else do we need? Yeah, we want it to be fast. Yes. Guys, but this is sort of, it's good to say. So, and it has to be, let us figure out what would be good and what would be great. Define fast in terms of good. Anybody wants to say?
Within 5% of STL stable sort.
Yeah, comparable, yes. Yeah. This is good. And now define great. What would be great?
Fastest existing node.
Specifically, observe that STL has stable sort and it has sort. Why does it have sort? Because it's faster than stable sort. All right? So the ideal thing, and let me tell you, that has been my dream for decades, but so far it's still a dream. So for decades, my dream is to make my stable sort as fast as my sort, at which point I could say there will be just one sort. And I make progress with stable sort, but then I make progress with sort. So we will look at sort eventually if this activity goes well, because it's fascinating stuff. But so that's what we want as fast or STD sort, right? Or, you know, that would be great. And I actually do not know. Let me tell you, by the way, that STL, present STL stable sort does not accept forward iterators. It does not accept bidirectional iterators. It requires random access iterators. Why? Because certain guy long time ago was lazy and overspecified the requirement. And then a year after, he sent a message saying, guys, I overspecified the requirement. Let us weaken it. It was never weakened. There's another thing that if you do something, it will never, I mean, bad decisions you make will stick with you, for the rest of your life. But let us try to maintain two. It's a really very tempting sort of thing too.
But as long as there aren't concepts, it's just a documentation error.
No. It's, you see that the difficulty is that is it a documentation, only documentation error? There might be places where it actually uses random access for dividing. There are a whole bunch of things which are overspecified, as we shall see. For example, in-place merge in STL requires bidirectional iterator. If you look at our implementation, which is the same as STL implementation, it's forward iterator. So why does it require? Who knows? Actually, I do know, and I could even explain. But you know, there are certain things, but it's some obscure stuff. So it wasn't carefully done. In general, you know, we have to understand that things which are published, even by reputable sources, as we shall see very shortly, might not necessarily be correct. So in order to do this, sort of use extra storage, but which merge are we going to use? Yeah.
So we start with, we figure out some threshold below which we should just do insertion sort. And let's say 8 or 16.
This is a great idea. Justify it.
Well, as long as things fit in your cache line, you probably shouldn't even do anything more complicated. Just do linear search to find where it goes.
Justify it. Why? Give the theoretical foundation for your statement. You're correct. But is it just hand waving, or are you on a solid theoretical ground?
Should I continue the algorithm, or should I first say why insertion sort at the low level is a good idea?
Do not do the algorithm. Explain why it is a good idea.
Because locality is good, and the simple,
Merge has a wonderful locality. For small n, n is better than n log n. No! This is just strictly false. Strictly false. Log n is greater than 1. So n log n is greater than n.
Always n is better.
No, but n square. N square is not going to be better. But, you're very close. You're on the right path. So one is going, let us see. What is the complexity of merge sort? How many comparisons does it do? N log n, yes? Anybody remembers what's the complexity of insertion sort? It's O of n squared, but O does not matter. What is specific coefficient? Okay. We're inserting,
As soon as you find an applicable spot, so on average, it can be faster.
on average, you're going to go halfway. On average. So how, altogether, how many things are we going to do? But we're going halfway, not of all the way. N squared over 4. Yes. So this is the important thing. N squared over 4. Now, when will this be less than this? Well, one would say that if log n is less than n over 4. Roughly. What is it roughly? 16. You were right. So the cutoff is 16. Approximately. That's what theory tells us. What should we really do? We should measure. We know that we shouldn't measure around 128. We shouldn't measure around 3. We should measure around 16. But this is something which we could easily do. So there is an algorithmic problem.
So we start consuming our power iterator and do just insertion sort.
And right here we have an algorithmic problem. Yeah, that's the problem. Can we? We don't need extra storage. Think about how do you do insertion sort. Let us revisit insertion sort. It's a wonderful algorithm. So we assume sort of it's a very simple algorithm. Let me remind you of how it really goes. Sort of it's an inductive algorithm. We assume that we sorted up till here. This is not sorted. So what do we need to do? We'll look back, I heard you say. That is the difficulty which we will have to face. We cannot really look back. We can do binary search, or we could do linear insert from that side as long as we're careful. So there are multiple. Again, I'm just pointing that we have interesting algorithmic problems implementing insertion sort. So why don't we write? We need to implement good insertion sort.
So we sort these things and we throw them into a binary counter and merge them.
Okay, so what Param is suggesting is getting rid of recursion. That's what your suggestion. Our sort is recursive. And binary counter would allow us to get rid of recursion.
I mean, I wasn't doing it to get rid of recursion. I was doing it to just make it easier to manage what to sort when. But
Yeah, but it will automatically also get rid of recursion. Yes.
But I mean, this will use the same amount of extra storage as recursion would have.
is to use insertion sort for sure.
Is that
when the n is below 16. That should be
okay,
ideal.
I mean, we have to write it.
Up 16 question mark. I mean, around 16, some number. We need to figure out. And then let me just, Param was full of ideas. Is he full of ideas every day like that? Amazing guy. No, I'm impressed because he cannot even type them as fast as you generate them. He said binary insertion sort. Or use binary insertion sort. We need to figure out, is it good or will it help or not? Remember, right now I'm taking this neutral, I'm just facilitating the discussion. I mean, in management circles, like whenever M team needs to come up with an important decision, they hire a facilitator. And facilitator is a guy whom you pay lots of money, who draws pictures on the board and facilitates the discussion to make them creative. So I'm just like that. I'm making you guys creative. So get rid of recursion using binary counter. What else could we do?
Actually, going back a step to using binary insertion sort might be, isn't that going to be better than just a regular insertion sort? So maybe the n would be useful for larger numbers than 16?
Well, it's for some n, yeah, he said.
So basically, I would say two separate ideas. One is use insertion sort for numbers.
Split 2 into 2 points. Use insertion sort or use binary insertion sort for n less than k. We don't know what k is. Why don't we know what k is? Because here, is it going to be dramatically bigger than 16 or not? Anybody wants to say? Testing. Remember, comparisons are important, but we're doing other things. When you need to do insertion, you need to move to do n over 4 moves. And these guys are going to be moved whether you do binary or linear insertion. But you could be right, since we are doing a trade-off. For n less than some k. Yeah. Okay. Any other great ideas, guys?
The fact that comparisons might be presumably expensive, but these moves might be pretty expensive. They should be expensive too.
Yes. Yeah.
That kind of makes the requirement of speed, measuring the speed, kind of tricky.
Everything is very tricky. But, okay, let me tell you one great secret when designing algorithms. When you design something, there this huge space of possible use, very big structs which you are moving around, very expensive comparison. Should you concentrate on that? The answer is no, guys. First, make your algorithm work really fast for what I would call a common case. What's the most common case? I would call doubles, because they're sort of big. You don't know what integers are. You know for a fact what doubles are. The size of doubles is fixed for centuries to come by IEEE standard. The size of ints, one computer is one, another computer is another. So I'm just sharing that you say, well, but it's just one case. It's always important to make your algorithms as fast as possible for the most common case. Things like double, things like pointers, right? Things like integers. Then, of course, we would need to test it for bigger things with different trade-offs and observe. But, we have a long path right now. So any other algorithmic ideas. You need to look through here because there are some things here which needs to go into up there. Because the ideas listed there, do not cover everything we listed in the requirements. Number 3. We still have not addressed that problem. How are we going to do that? How are you going to do that? We have to, again, what it means, we have to come up with some API, with some interfaces which will allow us to do that, I think. Okay? And then finally, let me mention just one interesting thing which everybody seems to miss. We need to see if we have a good merge. We assume that we know how to merge, but we actually don't. Maybe we do, maybe we don't. Okay? And you say, well, anybody could write a good merge. And here I want to show you something. And show it to them. Okay? If you go to Google and you Google for STD merge, it shows you this. This is the code, and since you are a normal programmer, you are going to say, it's on the web, therefore I could copy and paste and use it in my code, right? It couldn't be wrong. This is reputable. It's probably, I don't know, but John probably knows who maintains this page. This is the main source for, is the C++, what is it called? Show us the top of the page. C++.com. What is C++.com? It's like they tell you everything about C++. Now, let us look at this wonderful code.
It's actually saying the behavior of the function is equivalent to this bytecode.
Yes. Behavior. And I hope that it isn't. Why do I hope that it isn't? Because this is a broken piece of code. It doesn't work. It's not that it's slow. It doesn't work. Well, it sometimes does. Empty range will melt the computer. Right? Yeah, practical programmers, they don't. Right? It is an amazing thing. So, by the way, the homework assignment, let these people know this is not acceptable. There is a way. I mean, it is very embarrassing. It is.
I prefer using C++ reference, CPP reference. There's a better website. These guys are not maintaining it very well. There's a better one.
That's the first hit on Google.
That's Google's problem. That's not.
Okay, talk to your friends at Google. And the other one does not have that.
If the rest of us will start using the other one, then Google will figure that out.
The other one doesn't have it.
Two different possibilities.
It is a possible implementation. At least this seems to be correct. Is it good enough? I would say no. We will write better one.
Well, the purpose is to let someone know how it's being done. It's not necessarily to say, copy this and use it.
No, but it's, let us, yeah, I'm not criticizing them. How would they know how to write good code anyway? But let us, here we are to learn to write good code. So we will try to write a very, very good merge. Right? By the way, this is, could we go back to the ideas? So write a very good merge. I would put as number 4. And then you see we have this in-place merge. So how are we going to abandon this idea completely? Of in-place merge. That is, you see that what right now, if you read it, we use extra storage when the size is small. But when the size is not small, what do we do?
You use the in-place thing.
Up to a limit, we need to adjust, not just sort. We need to adjust our merge. So, and let us.
So we want to use different merges for different size data sets?
No. We want to use, Bert actually said it correctly. He said we need to use sort of copying merge while we can. If we can, it's recursive up to that limit. Sort of basically what we need to have is an algorithm which says I'm going to do this if I have enough memory, or that if not. Right? So it's the term which I use is adaptive. Right? So instead of, okay? So now let me, however, suggest, so how do we go about, there's just lots of things to do, right? So how would you go about, let us argue, how do we go about implementing it now? What is the first thing we need to do? The easiest thing.
We could write the merge that uses extra memory for small items, because we're going to need to use it.
This is a good idea, but that assumes, again, I'm very lazy. So, being a very lazy guy, I say, what is the first thing I want to do? The first thing I want to do is, right now I have a boundary thing. How, this is what the speed I could get if I have no extra memory. What's the other boundary condition? Yeah. By the way, what is infinite? How much extra memory do I really need to do all of that? Any other? So he needs 2 times. How much do you need? You need 2 times?
Plus an extra copy of each for each sub, each recursive call. No? If it's recursive. Oh, this won't be recursive.
So you still insist on 2.
As much as input
I think you could do with less. I think. Okay, let me just, I'm not going to tell you, but I'm just going to remind you of the one interface which we have. remember how we're doing merges? We have this, right now we have this thing divided somewhere here, right? And what we want, this is sorted, this is sorted, and then we want to merge it back. So what we get when we use our in-place merge, we get the thing which is sorted like that. Right? Okay? So what do you think? How much memory do we need?
If you have n over 2 extra memory, you can sort that first.
No, 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 we're not sorting, we're merging. You guys fixed your mind in this direction. Unfix it. You see, somehow you assume that you want to do merge into the extra buffer. Why? Yeah, it is half n, yeah. Why is it half n? Yes. Well, in our sort, they typically will be exactly equal sizes. We're splitting into 2. But even, I mean, in general, if this n1 and this is n2, how much memory do we need? We do not need n1 plus n2. Couldn't we get with less? Yeah, size of the first one should be sufficient. How would we do it?
Copy the first range out of the temporary storage and then just merge.
And then just merge. Yes. By the way, which will violate the requirement of merge. Because merge says that you cannot, these ranges should never overlap. Never mind, this is a wrong requirement. Of course, we could merge back. Of course, they will nicely fit into that. Here, we want the standard to fix the requirement, not to write bad algorithms. So, right? So we could do it with roughly n over 2. And that is my first suggestion, that let us try to see prioritize steps. Why I suggest, by the way, I claim that insertion sort is a very important thing, but we should do it after. Why do I say that?
It's more complicated. It's more, takes longer, it's more complicated.
No. 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 It's basically, there is a first rule is that you want to fix asymptotic complexity. Right? And doing insertion sort at the bottom is not going, right now we have a problem with our asymptotic complexity. It's n log square n. We want to get rid of that square as fast as possible. Oh, extra storage will do it immediately. Asymptotically. If I have extra storage, I will do exactly, believe it or not. Not fixed amount. Yes. No, 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 no. If I have enough storage, which is if I have n over 2 extra buffer, the problem will disappear. What do you mean it's not reasonable?
Too much.
Some point.
My machine doesn't only has a constant amount.
No, 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 but it does have constant amount of memory, but so does it have constant amount of stuff to sort. Yeah, yeah. Yes. So it will have a big immediate effect and will give us some idea where we are on the timing. This is where we are. Let us estimate the timing. Right? So my suggestion is that that's what we need. I mean, again, I shouldn't be pushing. I should let you do it. Maybe I overstepped my powers. But I would recommend first trying to see how we could use extra storage, because this is the sad fact. I mean, I know why I want you to do it, because I know that you will discover important APIs which you will be using later on. Okay, basically, we need to learn how to deal with this extra storage. And what I claim is whether this extra storage is fixed or not fixed, the set of APIs will be very similar. But no?
So the new merge that uses extra storage has to also define how much extra storage is available to work with.
Yes, and I would go in. This is my problem. Do I tell you the solution or not? Not? I agree with you. So maybe let's go eat pizza, since pizza is here and getting cold. And then we will try to do it. Because I will try not to tell you, because every time I say, I think this is a very good, we'll list, nothing is missing.
If we're going to requirement that we actually sort the thing?
Yes. Yeah, it should sort, yes.